All right, so continue to talk about basicity again. Again, thinking about these, we're really kind of focusing on nitrogen. Obviously, it could be other things, but we're just kind of honing in on nitrogen. Because nitrogen's willing to give up its lone pairs, act like a base. So two different factors here. We talked about resonance. Now we're going to talk about both substitution and hybridization state. So let's do hybridization state first. This is the classic one. You have a nitrogen that's an sp hybridized, a nitrogen that's sp2, a nitrogen that's sp3. Which one of these is going to be the best base, the most reactive base, is based on what hybrid orbital this lone pair is in. So in this case, if this is sp hybridized, this hybrid orbital is in a sp orbital. This lone pair is in an sp2 hybrid orbital, and this lone pair is in an sp3 hybrid orbital. Knowing the shapes of those hybrid orbitals, right? sp having, 50% s, 50% p character. sp2, 30 and 60. And then sp3, let me get a little bit more. There you go. Much more p character, 25% p character, 25% s, 75% p. The lone pairs in each of these, right? Which one's going to be more reactive? Well, the one that's farther away from the nucleus most of the time is sp3. The nucleus has positively charged protons. The farther away the electrons are from that, the more reactive they're going to be. So this will be the most reactive base, followed by the imine, and then lastly, the nitrogen, which has a lone pair in an sp orbital, right? Because of where it's located, the hybrid orbitals. So you need to know hybridization state, right? This is sp hybridized. That means it has two p's, two p orbitals, and two sp orbitals. sp2 hybridized, 1p, 3 sp2s, sp3, 4 sp3s. And the hybrid orbitals associated where the lone pairs go. Okay. Maybe a simplified version, but this is something to think about. Primary, secondary, tertiary amine. Which one's going to be the most basic? Which one will be the most basic? So if I did, we'll do this. A, B, C. So it actually is C. C is the most basic. Now the better question is why? Why is it the most basic? So there's two things competing here. Sterics and electronics. So somebody could say, which is not a wrong argument, could say, well, wait a second. So I'm looking at this lone pair for all of these. This one's a primary amine. Carbon's bigger than hydrogen. This is going to be able to get stuff easier because it's less sterically hindered. That's a reasonable argument. All right? That makes sense. What's the other type of argument? The other type of argument is an electronics argument, where it says, well, wait a second. Each one of these groups has sigma bonds and can do hyperconjugation, where it helps donate electron density towards that nitrogen. So the more hyperconjugation interactions, sigma bonds, 2 bonds away, the more electron-rich that amine will be. Perfect. So that's the overriding factor in this one case. So this has 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, sigma bonds 2 bonds away that can donate electron density. So that's going to make this the most reactive base. Now be careful though, because there's a limit to this. Notice how these are just methyls. I chose those on purpose. If all of a sudden I start doing stuff like this, now things get a little more complicated, right? Because now I've really changed the sterics around this nitrogen. And now this doesn't become so clear what's the most important thing, sterics or electronics, hyperconjugation or sterics. So just be careful, right? In a general sense, the more substituted, the more reactive because of hyperconjugation. But there's limits to that, right? And we take advantage of those limits actually to do some different things because of that. So just be careful with that. So we've done hybridization state, we've done substitution. Now we got to really start thinking about these are called heterocycles, things with nitrogens in the rings, and also relates back to aromaticity and what you know about aromaticity. So this, right, both of these nitrogens are what hybridization state? They are both sp2 hybridized. Right? Same hybridization state, so it's not so simple now. The question is, what hybrid orbital are those lone pairs in? So in this case, that's in an sp2 hybrid orbital. How do I know that? Because if you're sp2 hybridized, what do you have for hybrid orbitals? You have a p, an sp2, an sp2, and then another sp2. P orbitals are used to do what? Show me your p orbitals. They're used to make pi bonds. You have one pi bond. That p orbital must be used for that pi bond. Has to be. So that's off the table. So that lone pair has to be in an sp2 orbital. If it's in an sp2 orbital, can it do resonance? No, because you only do resonance in p orbital systems. So it can't do resonance. So that's not even a factor either, right? Here, this nitrogen's also sp2 hybridized, right? So it has the same hybrid orbitals, a p, an sp2, an sp2, and an sp2. Same hybrid orbitals. The question is, where is that lone pair at? Notice how this nitrogen doesn't have a pi bond. And this nitrogen is next to a pi bond. So it wants to do resonance, right? Things want to do resonance. So this nitrogen is going to choose to put this lone pair into a p orbital. It's going to choose to be sp2 hybridized. When it does that, it's going to allow it to do resonance. It's also going to be aromatic in this case. So the lone pair is in a p orbital and it's doing resonance and it's in an aromatic ring. Is this one then going to be that reactive, that basic? No. Because it's doing resonance, first of all. But then also, it's in an aromatic ring doing resonance, right? And we don't want to break up aromatic rings. Those are really stable, right? So understanding hybridization state, but also then what hybrid orbital these nitrogens or these lone pairs are in is really key as well.